Okay.
Cool. I think I'll start. Hey everyone. Hi, welcome back from the coffee break. We'll start the last part of the workshop. So it's my great pleasure to introduce Professor Shuran Song. Shuran is an assistant professor in the electrical engineering at Stanford. She recently moved from Columbia University. She directs the robotics and embodied AI lab. And she does a lot of cool stuff in perception, learning, manipulation. She received several awards, including NSF Career Award, Sloan Foundation Fellow, and several paper awards. So I'm so excited to hear her talk.
Great, thank you. And thank you, everyone. Hope you drink coffee and are fully caffeinated and ready to hear my talk. Yeah, so today I'm going to talk about policy representation for robot manipulation. So we know that this workshop is about neural representations, right? So I want to start my talk just by having like a little bit discussion about why we care about representation. And I think there's really like two main reasons that's why we care about that. Is there a way that I can, I think maybe here, okay. Two reasons why we care about representation. I think first is that with the right representation or the right choice of representation, we can oftentimes encode the right inductive bias in our learning framework and therefore make the learning easier. Right, so I think the canonical example people like to use is these different representations of our solar system. Right, so both of them, you can see that they can correctly expand our observations, but one of them is centered by the sun, the other is centered by the earth, and then one of them is actually much easier or like able to kind of generalize better to other physical process. So yeah, so in this case, both representation can correctly describe observation, but one is more informative. And another reason that's why we care about representation is that the right representation oftentimes come with much bigger or stronger expressive power that is able to allow us to encode more information. Right? So that's not about the inductive bias to make your learning easier, but just about amount of information that you can encode in this particular representation. Right? So here is the examples of two types of 3D representation that you can use to represent your 3D geometry. One is voxel, the other is implicit neural representation. So in this case, both of them are representing the same underlying geometry, but one can potentially encode infinite resolution. So that is another goal or properties we want to achieve with the right representation. So this is actually slightly two different goals or ideas. One is actually use the right representation to encode the right inductive bias. The other is to make the representation as expressive enough, even without the right inductive bias, but just so that you can encode all the information. So today my talk will actually going to talk about more on the property that's trying to make our representation of the policy as expressive as expressive as possible, so that they can encode most general robot manipulation behaviors. Okay, so when we narrow down to the problem of manipulation, when we talk about representations in robot manipulation system, oftentimes the first thing that's coming to our mind is to think about representations, the input and output representation. So for example, there is a lot of work that kind of studies the impact of action representation. You can choose different output formats to represent the same robot trajectory or action. Either use joint or end factor space, choose to use position or velocity control, continuous or discrete space to represent different robot actions. And in practice, all this choice or decision does have a pretty important impact on your end system performance. And then even more often, we often see people study C representation for the input or like the state representation. I think that's probably most of the talks that you hear about today is kind of focused on this category, thinking about what is the right representation or how we learn the right representation so that it's both informative and expressive to represent the environment, so that the robot can infer action from that. But I think there is something missing if we're just thinking about the representation for the input and output, right? So that is actually in the middle, the policy representation. So oftentimes, I think for a very long time, the policy is just represented by whatever default neural networks that you have. And then it's a feed-forward network that input states, output action, and that has always been the default solution. And then on top of that, as a community over the past decades, we actually studied so many different learning paradigms with these default options, right? So for example, we studied like imitation learning, meta learning, or reinforcement learning. But if you look at it, the ultimate product of all these different learning paradigms are the same. It's a visual motor policy that is able to infer action from observation. So no matter how the representation itself is not expressive enough, it can easily limit any kind of learning paradigms. So however, on the other hand, if we have a sufficiently powerful policy representation, we start to realize that even very simple learning paradigm, or in other words, the simplest possible learning paradigm, behavior cloning, can perform very well. Right? So that is actually a finding that we kind of observed in one of our latest work called diffusion policy. So I think we are, first of all, not the first group that studies the policy representation. There's actually a lot of prior work, well, actually not a lot, but there are some prior work that's actually studied this problem of different policy representation. And I think one of them I really want to mention is this implicit behavior cloning paper that actually is largely inspiring our work on diffusion policy. So in this work, I don't know whether Pete is still there, but Pete Florence is the first author that's kind of, they propose a very simple idea by just changing the representation of the policy. Instead of this simple feed-forward network, you can change it into an implicit formulation. That's this network actually taking both observation and action as input and predict energy value for this pair of observation and action, and take the output in order to get predicted action, right? By just doing this very simple formulation change, what they show is that you all of a sudden is able to represent a much larger categories of distributions, or that include, for example, discontinuous distribution or multimodal distribution. This turned out to be very useful in modeling robots' behaviors or actions. So today, I'm actually gonna just tell you a work that's kind of like the follow-up work for this implicit behavior cloning. And basically, the question we are thinking about is how we can rethink about the policy representation or using other policy representations to improve the overall visual motor policy learning. And then that is a work called diffusion policy. So you can see that it's actually, on this side-by-side comparison, you can see that it's actually taking a lot of ideas from implicit policy that we also kind of learning some kind of energy function from the observation and action, but actually the major difference is that we're learning the gradient of this energy space. And then I will talk a little bit more details about this approach in the following slides. So this diffusion policy is actually a joint work with both TRI and MIT. So first, before showing you the actual method, I want to just highlight to you the results of diffusion policy. Right, so here is actually a variety of tasks trained using the same network architecture, and all the policy is directly inferring action from the pixels, right, the raw sensory input. So what is diffusion policy? I guess most of you guys are very familiar with diffusion models for image generation. Right? So here we are using something very similar, basically the same idea, but apply it for robot action learning. So we basically try to train a generative model that's able to infer robot action conditioned on visual observations. And in this particular example, the robot action is represented as a 2D sequence of unstructured positions. Right? So the dots is representing the actions, but you can represent the robot action in 6-off or 3D space as well. But for this simple example, the action is just a 2D sequence of positions. So concretely, how diffusion model works is that we'll start with a random sample, a Gaussian sample of action, and then we'll train a neural network that's try to predict how to remove noise from this sampled random actions. Right? So this prediction network is conditioned on the visual inputs from the robot. And then after a few of these kind of denoising steps, we'll hopefully get a clean action that is executable by the robot. And then this whole process, this whole denoising diffusion process is our policy representation, right? So it is not just this network is diffusion policy, but instead this whole iterative evolving process is diffusion policy. And then you see that this diffusion policy at the very high level basically taking visual observation and output action. And then this whole policy will run in a closed loop format and is able to run at around 2 Hz so that you can get a reactive closed loop behavior in the end. So with this simple formulation, we actually surprisingly found that diffusion policy is able to simultaneously address a number of challenges in policy learning. Right? So for example, action multimodality, which means refer to the scenario, giving the same visual observation, you may have multiple valid actions that you can execute in that scenario. Right? So for example, in the simplest case for this push key task, is that you can both go left and right and both of them are valid action. And then although this is a very easy example to think about multimodalities in action, you'll find that this kind of multimodality problem actually exists quite common in human demonstration data. And if you look closely on almost any task, you will actually observe this kind of multimodality issue. So for example, at this stage, the robot have the choice of keep pushing the key or go back to the target, the original position. And similar for digging the cells, they can choose whether they continue to dig more or actually stop the action. And then if the policy actually is not powerful enough to handle this kind of multimodality, the simplest behavior that you'll observe is that the robot will stuck in that location, but not performing any action because they don't know which direction to go, which is a pretty bad behavior that we really want to avoid. And then part work actually, there's a lot of work that's trying to address this action modality problem. And so 2 typical ones is you contest your action space or use a mixture of Gaussians. And then I think different, regardless of how you, like both of these part works, what they try to do is basically try to approximate distribution with either contest action space or mixture of Gaussians. So as a result, it ultimately limits the precision of the output representation that cannot really precisely represent the multimodal distribution in action. But on the other hand, I think diffusion policy is able to theoretically represent any bounded distribution, including the ones that are discontinuous, picky, or multimodal. So I think conceptually or intuitively, the way that you can think about it is that because each of the steps that diffusion policy is predicting the gradient on the action, we are actually basically doing the gradient descent on the action space. So as a result, if you like in the gradient descent process, they can easily stuck in local minima, where each of the local minima basically captures a mode. Right? So the stucking in local minima problem is actually a good thing in this scenario because now we can easily model different modes in the action space. So here is a quick comparison compared to prior works on handling action multimodality. You can see that prior works either only models like only able to capture one mode, or they're actually isolating between different modes, which is even worse. And then apart from the ability to model the multimodality in output action, diffusion policy is also actually very scalable to output action dimensions, right? Because people use diffusion policy to generate image, which is a very high dimensional space. So it has no problem on outputting a high dimensional output. So because of this advantage, we can actually easily afford to predict a long action trajectory instead of just predicting the next action for the next time step. So this kind of action sequence prediction also allows the algorithm to ensure or kind of guarantee this temporal consistency, and then which actually is pretty important in handling, in avoid this kind of oscillation behaviors between different modes. And then finally, diffusion policy is also very stable to train. It is actually a pretty important and practical benefit for using diffusion models instead of other generative models for modeling robot behavior. Because when you training a robot policy, and if you have a very unstable training, means that if you take different checkpoints on different times, you will get very different performance. Right? At some point, it's almost a perfect policy. At some point, you get like a really crappy policy just because you choose the wrong checkpoint. And then in robotics, choosing the checkpoints oftentimes means that you need to deploy your policy in real world, and then that's a very tedious problem that you probably don't want to do it a lot of times. But your diffusion policy is actually very stable, means that you can pick any of those checkpoints and you'll get a reasonably good performance. So that's actually a very important and practical reason that makes diffusion policy a good framework to use for learning robot behaviors. So in our paper, we perform systematic evaluations on many different tasks and benchmarks. So in total, we test on 12 different tasks over 4 different benchmarks. That includes both simulated and real-world environments. That's test on single and multi-task benchmarks using rigid and fluid objects with the data that's collected by single and multiple users, right? So this is actually an important difference, because when you have multiple users collecting data, you're more likely to observe multimodalities in the data set in the collected data sets, because different people may have different conventions of doing the same task. So what's kind of surprised to us at the beginning is that we realized that diffusion policy is able to give us a very consistent performance boost regardless of task we test on. Right, so here I'm showing you the best performing algorithm from each of the benchmarks. It's actually not the same baseline. We always pick the best from different benchmarks. And then regardless of which task you're testing on, diffusion policy always able to give you a little bit of performance boost. So that probably means that you can think about diffusion policy as a drop-in replacement for any of the policy that you're training on, and you can probably very likely to observe a performance improvement. So after we publish this paper, our friends in TRI or collaborators in TRI actually take this framework and scale it up for many different tasks. And then they're actually able to achieve many challenging manipulation behaviors or tasks just by using this very simple framework of training diffusion policy with behavioral cloning method. So I think that's why you should maybe also try out on your task as well. So we actually released a code base for diffusion policy, and in particular, this Colab tutorial is a very simple example that's within just 1,000 line of code. You can actually go through complete examples of diffusion policy and understand what is the main ideas or key ideas for diffusion algorithm, and then you can apply it to your task or system afterwards. But before you try it out on your task, I do want to mention 2 limitations about diffusion policy so that you can get prepared. So these 2 limitations, one is about data collection, the other is about the task formulation. So first, for the, let's see what I have. Yeah, no. So for data collection, right now, the way that we are collecting the demonstration data is actually using a quite non-intuitive operating interface. Right? So we are actually using the space mouse to collect training data for this map frequent task. If you just think about how you're going to tally out a robot to do this task, it's really not trivial. It's actually required to mentally compute inverse kinematics in order to know like what is the action that is possible. Right? So far, only Shuran in our team is able to tally out this task. So I don't think that's a very scalable solution. So if you want to use diffusion policy, maybe the first question you want to ask yourself is that, is expert demonstration easy to collect? Or is that, are you able to collect expert demonstration? And another limitation is that diffusion policy, at least in the current formulation that I just talked about, is actually a single task policy, which means that you need to train different policy for different tasks, and they cannot be shared across different tasks. Although this thing is actually, I think both of them is possible to address, which I'm going to talk about a little bit about potential solutions for those limitations. Yeah, so the work that we actually work on a number of projects that's trying to address that 2 limitations. But today I'm just going to highlight one of the works that we worked on and also published in this conference call. It's called Scaling Up and Distill Down. So as suggested, this work actually has 2 parts. One is scaling up data collection in simulation, and the other is to distill down into a lightweight visual motor policy that you can deploy it on the robot platform. So in the first part, in the scaling up part, we're trying to address this data problem by using large language models and simulation state to scaling up the data collection. Right? It's basically given any new task that the robot has not performed before, we'll